go to the introduction to counterparty credit risk. Now you may wonder, why is this 17? The reason is, of course, we labeled the slides according to, or the sections of the slides according to the chapters in the book. And chapter 17 in the book is concerned with dynamic portfolio credit risk models and counterparty credit risk, because it turned out that counterparty credit risk, if you really want to treat it in a model-based way, requires you to have a dynamic portfolio credit risk model. And it is under the special topics. Under other special topics are multivariate time series, multivariate extreme value theory, and other things. Now here we do only counterparty risk, and I also will not do too much technical stuff. So the introduction is probably going to be most important, and I want to show you a nice R script by Alex. Good. Now, a substantial amount of all derivative transactions is done over the counter. What does that mean? That means that whatever, if I do an over-the-counter swap with Paul, when we two just do a deal and we promise an exchange of cash flows, say an interest rate swap, Paul promises me to pay fixed interest rates, maybe 2% every 3 quarters, and I promise him to pay floating interest rates. However, there is nobody who guarantees these payments. If I default after 5 years, then Paul has just bad luck, and his obligations towards me remain, but mine are sort of gone, and he might make a loss. And in particular, swaps are still very much over the counter, because the alternative is exchange traded. When you have an organized exchange in between, then you have a system of margin requirements and so on, and you're trading not directly with Paul, but we would have the exchange standing between us, and this exchange would guarantee that Paul gets his money even if I default. And to be able to do that, they use margins and so on. That is, of course, nice because counterparty risk is gone, but if you trade over an exchange, it also means that you're sort of tied to standardized contracts. You cannot have an arbitrary variety. In particular, interest rate swaps are, of course, very much typically tailor-made, because if Paul is whatever, a bank or an insurance company, and he has certain financing needs, he has certain day and a certain nominal and so on, what exactly he wants, and this will not exist at an exchange. There's another very important product, if you want, that is done over the counter without exchanges in between is, of course, reinsurance. If you do a reinsurance deal, there's also nobody who guarantees you that the reinsurance company will actually pay. They might default, and then you will have to make a loss, and you will have to replace your reinsurance contract. And this risk that in a deal one of the two parties cannot pay because cannot fulfill their contractual obligations, that is known as counterparty risk. Of course, it has always been there, but it was treated a little bit in a cavalier fashion very much in practice until the financial crisis, when all of a sudden people realized, due to the default of Lehman's, that this can really happen, that it's really possible that a major derivatives dealer, for instance, defaults. AIG was also very close to default, and one of the reasons that it was safe was that it was such an active dealer on the credit default swap market. Before that, counterparty risk was considered, but sort of only in a one direction. Banks were worried about the counterparty risk to their trading partners, but sort of the trading partners had to assume that the banks were default free, which was not 100% correct, as we learned. So this is very important. It is a major concern. It has made its way into regulation, both Basel and solvency, and that's why we thought it would be good to conclude the whole thing with a few words on this risk. Yeah. Now.
Sorry. I mean, what Alex was doing this morning. I mean, this was.
It's also in a sense of counterparty risk that he was considering loans which are not being paid back. Yes, of course. So that would be a special example. Also, What is probably new is the thing that it's now much more symmetric. What I just meant is counterparty risk. And the one thing, a bank gives you a loan and then the bank is worried that you don't pay your money back. That has always been there. But the other way around, that sort of you are worried that the bank doesn't pay your money back. It has been a little bit there. We have, I don't know, what is it, deposit insurance, and these things are there, of course, to guarantee this, but it has not been considered as something. I mean, you have risks and risks. You have some which you believe in and others which you sort of.
But why would it be treated mathematically differently?
No, it's not treated differently. It's just getting more extent. Okay, what is different? Good. Or what is more complicated? One of the things that make counterparty risk management complicated, and that brings me to the next slide, so that's a nice question, is the fact that you do not really know. Your exposure is much more random. I mean, there's also some randomness in loans because it's not always you have credit lines, and so if your bank gives a credit line, you do not know if the other side will take the credit in full. But when you have a normal loan like a mortgage, then you know your exposure. You have given this guy whatever, 1 million Swiss francs so that he can buy a home, and that's your exposure, and full stop. And in this world of derivatives, this can be different because you do not even know if you really will in the future have a counterparty exposure or not. And this brings me to the example of an interest rate swap, which we'll then also look at a little bit more in an R script. So in an interest rate swap, you have two parties, A and B. It's a pity now that I know how this works, we have to stop. Good, so we have two parties, A and, let's go a little bit more to the middle, A and B, and they exchange cash flows. And just that we understand the script sort of, A pays something to B and the B pays something back. And in the example we are having here, A receives fixed payment and makes floating payments at predetermined time points every 3 months. Starting maybe by the beginning of 2017 and going 20 years into the future. These things go that long. That's also one of the reasons why it's so important. So even if whatever Paul and I are doing these contracts, we both seem to be in perfect economic shape right now, 15 years down the road, this might change. And that's what we consider. Floating is typically LIBOR rates. So, and this can, of course vary. That's the type of contract we are considering. Now, these swaps, similar to the credit default swap, they are done in such a way that the fixed rate, that's also the swap rate, this is fixed in such a way that at the point when the two parties agree on the deal, the cash flows from A to B and the ones from B to A have the same value, so that there is no money being shifted around. But of course, this is going to change over the lifetime of the contract.
Because the swap rate is a famous discussion also in the Swiss solvency test as a possible default-free rate or a risk-free rate. In comparison, there was a big discussion in life insurance between using government bond rates or swap rates. That's a famous swap rate.
And it's used a lot for longer-term horizons where bonds are not so frequently traded and where corporate bonds are also, not even government bonds are subject to all types of liquidity stuff and so on.
So these consistent for market consistent value.
Yeah.
So these swaps would have longer time horizons typically than the CDS, for example. So
yes, a swap can go over 20, 30 years easily. But they are mostly used for interest rate risk management, and so that's why they have this long.
Yeah, that's what people need, but
yeah.
Not in all areas you get what you need.
No, that's why they are over the counter.
Okay, I see.
You have to go to another bank, and then ask them to do this for you.
They always can give you one, but you have to pay.
I still have vouchers. I can pay by vouchers.
Well, I think that's going to be a pretty one-sided market in this SAV vouchers. It's like this carbon dioxide certificates close to expiring. Somebody will have to drink 100 coffee now. Okay, but back to the story here. I want to come back why this is different. Good. Now, the value of this contract will change according to the changes in this interest rate. And at any given point in time, I can price it if I know the value of all future zero coupon bond prices or yields. But of course, when the interest rate curve changes in the future, the value of the swap will change. So let's assume that interest rates are, which is the first one, yeah, that interest rates rise. And now we consider the whole thing from the situation of B and look at his sort of P&L that he has with the swap. So if interest rates are rising, he receives floating, so he will receive sort of more higher payments, and the value of the fixed payments he has to make in the future will be lower because he can discount them at a higher rate. So the value of this, but they are, I mean, the floating will change. The fixed is, of course, there. That's in the swap, encoded in the swap contract. So the value of the swap will be positive for him. If, on the other hand, interest rates fall, the value will be negative for him. We see a picture for that soon. And then it really depends. Now, assume that A defaults. And now it depends really on the realization of the interest rate if B makes a loss or not. So if R goes up, then the value of the swap is positive. And hence, if A defaults, if R decreases, then the value of the swap is negative for B. And then while it won't come handy, he will still have to pay, but he won't make an additional loss. He will be forced to realize the loss he made on the swap deal, but he has to account for this anyhow, but he will not make an additional counterparty risk-related loss. He will just be forced to realize his loss and pay this into the bankruptcy pool. So there is an economic loss on the underlying transaction, but that has nothing to do with counterparty risk. He just lost on the transaction, but there's no counterparty loss. And the size of the exposure, of course, also depends on how much the interest rate moves. So that is the one thing that is really different. The size of the potential loss depends on, is quite random. If you have one or not and how large it is, depends on the economic environment. And, okay.
At this point, that there's no upside for B is in the default. It's quite interesting.
Yeah, in the default, there's no upside. Of course, yeah. The thing can also go the other way around. And that's one thing to take into account. And if you really want to model this nicely, you also have interesting questions on how the default time and the economic value of the contract are linked. Maybe if these are interest rates and you know that the one of these guys has a very strong exposure towards interest rates from his core business, you cannot assume that these things are independent. And we also come to that a little bit later. But before, I want to just show you a nice R example Alex has made to illustrate this point with numbers. It is in the repository in Chapter 10. So we will price an interest rate swap in the CIR model. So we assume that the short rate of interest follows the Cox-Ingersoll-Ross model, exactly the same as we've just seen in credit risk. And we will see how the value and the counterparty credit risk evolves for the counterparties depending on the realization of the interest rates. Good. This uses also this STE library Alex mentioned yesterday, which you can use to simulate paths. we consider a Cox-Ingersoll-Ross model. You can just write this still down here. dRT is equal to kappa times theta minus RT dt plus sigma square root of RT dWt. Good, that's what's done here. There is a small twist also we need to consider. This is nicely done in this example and relates to what I mentioned before with this picture. We need P and Q simultaneously. We need it's interesting if you want to do risk management, the P dynamics of the short rate to maybe evaluate the loss distribution of the swap, and we need the Q dynamics of the short rate to be able to value the swap in the future. Today, we can read, pricing a standard interest rate swap, you don't need a model for that. You can read the price off if you know the prices of future zero coupon bonds. You can discount the fixed payments and the floating ones. You just invest one unit of account and roll it over. But if you want to value the thing in the future, it will depend on the future yield curve, and that will depend on the future interest rate. Good. So that is, I already ran all these things. So there's a P and the Q dynamics of the interest rates there. And then we have this pricing function for zero coupon bonds. There's an A and a B. These are the functions which I just showed you on the slide. They appear also in interest rate modeling. And then now we can price the bond and we can compute its corresponding yield. The current short rate is 5%. And then we can simulate oh, sorry, yes, it's a realistic example. There's one X. Yeah. Whatever. Good. Then we can generate 20 paths of this interest rate in the future over half a year using this package. And what we're going to see are the first few days of these various paths now. I'm going to plot them for you. That's the next picture here. So, by the way, you see that R works also under Windows. I have the R Studio for R under Windows. And these are now 20 different interest rate paths. They all start at 0.5%, and then they wiggle around until 0.02%, and some of these paths are also rising. Now we consider such an interest rate swap which pays the tau equal to 0.25, means that we have quarterly exchanges of cash flows. The nominal is, I think, 1,000. And, well, we don't have to go through all of that here. And we can price it if we know the current yield curve. Good. That's the next thing. Then, as I said, for pricing these things, the fixed rate, the swap rate, is determined in such a way that the value of the contract at time 0 is 0. That is just done here. Good, and I need to print it for you. No, sorry. To go down here. So the swap rate would be almost 1%. So that would be the fixed payments we have to put in so that the value of this contract is actually 0. Then the next picture plots for you the value of the swap corresponding to each of these 20. I have to do this one first. Yeah, that's too fast. Well, let's do all of it. Good. Okay, so that is the plot of the swap. As seen from B, that's exactly as in this example here. For each of these different interest rate realizations, we now get also a trajectory of the swap value. they look very similar, but the scale is, of course, completely different. Good. Can also compute yield curves. Let's just do it. That's not really necessary. Okay, and now to illustrate the point which I made before, what happens to the swap depending on the realization of the interest rate, we're going to consider two scenarios. One where interest rates rises, that is path number 16 here, and then one where interest rates are falling. Okay, maybe make it slightly bigger. So what we see is here the interest rate, here we see the corresponding value of the swap, and here we see the change in the yield curve over time. So the black one is the original one, and the red one is, no, that's the bond price, not the yields. The bond prices, because they are decreasing if interest rates rise, and the yields come then next. Sorry. Now down there we have, I don't want to export it, I just want to zoom in. Now we see the yields, and we see it's almost this duration model with parallel shifts, so it's not that bad, which we looked at. But here it comes really out of a fully fledged model, even a very simple one, for interest rates. Good. And you see really how the swap increases in value. So that would be the scenario where if the counterparty A defaulted here at time point 0.4, we would make a loss of whatever 4 million or so of the underlying currency. Kill this. And similarly, when interest rates fall, that's the seventh realization. Can plot the same stuff. So here you see the interest rate, the swap value, the change in bond prices, and the change in yields. Now yields go down. The swap has a negative value for B, and so he has no counterparty risk loss. And the size of the loss depends, of course, also how large the interest rate is. So this is just to illustrate that point and to show which is sort of different or particular for counterparty risk management, that the size of the exposure really varies. Good. Okay, now a few general words, not too quantitative, about the management of counterparty risk. What can you do to mitigate it or to deal with the issue? There are a lot of techniques, some of them quantitative, some of them qualitative. One issue that arises, you need to take it into account in pricing, or that is currently being done, and I think it's even forced, at least in the Basel regulation. You have to compute so-called credit value adjustments, which take into account that the derivative may not be worth as much as you think, because maybe your counterparty doesn't pay you. You can control it via more or less quantitative techniques. An important issue is netting. Now, typically, two banks do not have only one swap between them, but many different products. And if they have a netting agreement, what they will do is they will first, in case one of the two defaults, then they will first compute the P&L on the aggregated portfolio, and only if the aggregated value of all contracts between them is sort of positive for one of the counterparties, he makes a loss. Without a netting agreement, so to say, I have two swaps with Paul, and sort of, I have one swap where I pay floating and receive fixed, and then I have sort of the opposite deal as well, so that they almost cancel each other. And if we do not have a netting agreement in the by default, then I will have, and then I will make sort of a gain on one and a loss on the other. I will suffer a counterparty risk-related loss to the one on which I made a profit, and I will have to pay the other one in full. If we have a netting agreement, we can net them first. They will almost cancel, and the remaining loss will be much smaller. These are netting agreements which you have, which are important. Another important thing is, of course, collateralization. As organized exchange do it with margins, we could also do this amongst us and have collateral, cash, or relatively liquid securities which we move around according to the economic value of the contract. That can reduce the potential loss dramatically if it's done correctly. It will probably not do it perfectly because it always takes some time to adjust the collateral. I've written an interesting simulations. Well, I think a simulation study on this which some people find interesting. But it's definitely a very important technique. And collateral is, many things have to be collateralized by now, and there are large amounts of securities and cash which are being shifted around.
Excuse me, with a netting agreement, I mean, normally when you get into a swap, it's because, for example, you just want a fixed cash flow which has no volatility any longer. But then if you put this netting offset, I mean, you're back to square one. I mean, what's the purpose?
Well, if you're a bank, you have maybe, or there are many reasons why. If you think about examples of the credit default swap market, I think 80% of all these contracts more or less canceled. Sometimes because people speculated on a price evolution. So, for instance, when you, and similar for interest rates, when these deals are being made for speculative purposes, then what happens very often is that you do one deal, and then maybe not, you will not reverse it immediately. That would be pointless, as you say, but you maybe reverse it 3 months later or a year later because then interest rates have risen, you've made your profit, and you want to cancel the whole thing. And these things do exist, or you have a big institution like a bank, and maybe desk A has one view on the future, desk B has another one, and one desk is speculating, and that's why it takes one position. The other desk is just meeting consumer financing requirements and has the opposite position, and they have very often no clue whatsoever what the other guy is doing. I remember, it's not a funny, it's a sad story, but it's still somehow funny that people at Citibank who made the structuring of all these CDOs and mortgage-backed securities and so on, I mean, they knew themselves that what they were doing was increasingly shaky, but they were surprised that there was still demand, and only after the crisis had on, they found out that this was something that they really sold it to some entity which belonged to their own company. And then, okay, so it can really happen that a big institution has many people taking positions, and some of these cancel. I think the most important reason is really that they speculate on a direction and then offset the thing not immediately, but maybe half a year later and so on. And when you have a netting agreement, only the remaining things change. Only the net position matters for counterparty risk. Good. A few to sort of conclude. As a final bit, I will say a few words about this valuation adjustments, credit value adjustments, and about some simplified formula which is being used in practice. So the general definition of a credit value adjustment is of the following form. The true price which you really should charge is equal to the counterparty risk-free price, sort of the price that is correct at first order, minus adjustment for, this is for the special case of, you can say, of a credit default swap, and you view this from the point of view of the protection buyer who makes the premium payments and gets the fixed payments. But the same thing and the same definitions would work for any interest rate swap or anything, but to be specific, we consider here the case of a CDS to know who is who. But if you just exchange notation, it works all the rest. So the true price, the counterparty risk-free price minus the adjustment for the default of the seller, because from the point of view of the protection buyer, the contract is worth less if the seller may default beforehand, plus an adjustment for the default of the buyer. Of course, you could do exactly the same with a reinsurance contract. If you're an insurance company who buys reinsurance, you're the protection buyer, and the reinsurance company is selling you protection, and you would have exactly the same type of adjustments. So that's how they are generally defined. Now there's a whole zoo of these things, and in the math finance literature there you have titles where you call them XVA, and for the X you can put in whatever you want. It depends on if the deal is collateralized or not, and if you consider it symmetric, so bilateral or not, and sometimes people also consider funding value adjustments. I'm not going to go into that, we decided also in writing the book that we have one type of adjustments we discuss. There is more to do, but only in the future when the dust has settled and when it's clear which of the adjustments will remain and which ones not. So we consider just two here in this text, the credit value adjustment and the debt value adjustment, assuming that there is no collateralization going on, but this can all be extended. VT is the market value of the credit default swap, or if you want, also the market value of a reinsurance contract from the point of view of the protection buyer, and the market value under the assumption that B and S are default free, so that the cash flows that are written in the description of the contract are also really taking place. Then we have here, for this example, 3 potential default times. The reference entity can default, so the person on which the default is written, or in the reinsurance case, it would be the time when the claim really happens. There's the default of the seller, the default of the buyer, and tau is the minimum of these. And that is sort of the interesting default, the interesting time when something happens. And psi is just the identity of the first defaulting firm. So if psi is equal to S, it means that protection seller defaults first. And we use X plus as the maximum of X0 and X minus as the minimum. And D of 0T is a discount factor, so you can consider with. And then one has the following general formulas. This is just basically accounting, but it's an interesting formula. Let's consider the credit value adjustment. The credit value adjustment is it's a pricing adjustment, so it's under Q, and you have to pay something provided that first, or it has some value. Tau happens before T. If tau is after T, then sort of the contract goes its natural way. The credit value adjustment also is an adjustment for the case where the protection seller defaults first, so where the protection buyer potentially makes a loss. The loss is proportional to the value of the contract, to the positive part of the value of the risk-free value of the contract at the first default time. That's as in the example of our interest rate swap. If at this first time tau, if it's the default time of the seller, and if the swap has a positive value, then I will make a loss. The loss may not be the whole exposure because maybe I get 50% because the seller can pay me still something. That's a loss given default of the seller, and that's discounting. And similarly for the buyer. Now, a few comments. They are also on the next slide, but it's maybe better to make them while these formulas are still here, at least some of them. What we see is that essentially what we have to do to compute this thing is we have to price an option with strike 0. It's a positive part of the value. So it's either 0 or the positive part. So we have to price an option on the value of a credit default swap, or on the value of a reinsurance treaty, or on the value of an interest rate swap. And an option with a random maturity. Why default free? That's a little bit of a convention that one says, okay, the loss is in principle, you could say if I replace it, I have another counterparty risk, but then you get counterparty risk squared, and you think that this is then small. So one just, to avoid these recursions, one typically takes the default free value there, because the probability that this happens should be small, and then if you take it, sort of, you get this probability squared. Good. So you have to look at an option on this thing. So this sort of means that if you really want to compute this in a formal model, the model you will need is at least one level more complex than the model you need to compute the underlying thing. For instance, to price an interest rate swap per se, you don't need really, if you want to price it now, you don't really need a model for that. You can read off its price from the term structure of interest rates. To price a credit default swap, you don't need much. These very simple hazard rate models, which we had yesterday, are enough. To do this, you need more. You need really a model for the dynamics of this value. So you need a term structure model to do this as the one I showed you, sort of as a very simple case for the interest rate swap, or you would need a dynamic credit risk model in the other case, or you would need some model for the evolution of insurance premia and the value of a reinsurance contract if you wanted to do this for reinsurance. And you need not only that, if you want to do this really properly, you need sort of also a model that takes into account the dependence of the default times of these guys and the value of the underlying contract. So this is relatively complicated if you want to do it properly, and that's why all sorts of approximations are out there. I think, yeah, that's basically most of the comments that are here. Yeah, credit value adjustment gives a loss of B due to premature default of S, and the other way around for the debt value adjustments. The value adjustments are like an option on the market value. It works for all types of derivative. A last point, the credit value adjustment is okay. The debt value adjustment is a little bit perverse. It means that your own liabilities have a lower value if you're less likely to repay. So if you're a bank, your credit rating goes down, your spread goes up, it means that your liabilities have a lower value because it's not so likely they're going to repay them. And that is a little bit perverse there. There's a discussion, that's why if debt value adjustments is really the thing you should do. This enters, well, there one comes into this weird world of accounting, and well, it's a world which we should leave as quick as possible. But no, one can't, and I think accounting for proper economically sound accounting for derivatives is probably one of the most challenging questions in this area.
There's one interesting area, which especially for life insurance companies is important. Take the example of Greece, government bonds of Greece. What constitutes a default?
And that's in this
political decisions, and so I think a lot of life insurance companies, of course, were starting to buy the default swaps on Greece defaulting, as an example, in the crisis or the end of the crisis, whatever, 2 years ago. Default was not really uniquely interpreted by the courts, so that these adjustments are really very tricky. It can cost a lot of money to the underlying companies, especially life, not just life, but particularly life insurance.
Yeah, I think in the corporate case it's pretty clear with all these ISTA regulations. A number of cases have been there, but it was probably there. But for sovereign bonds, probably these things always have to go to court once before you really know what they mean, and then you have different legislations there and all these things.
Can I ask something?
Yes, of course.
Just one slide before that. What is the delta?
The delta is the loss given default.
Okay.
Because you may get something.
Yeah, okay. A fraction.
Yeah. Okay, so these are these comments here. Yeah, I think we finished just in time. As I said, we need simplified formulas to do that, and one way of simplifying this formula, which is being applied a lot, is to assume that as I said, to evaluate the CVA and DVA formula correctly, you need a model with stochastic credit spreads that takes the dependence between the default of SB and the market value of the CDS into account. So this would mean a dynamic portfolio credit risk model. And because you need a dynamic portfolio credit risk model to do it properly, that's why you find the counterparty risk at the end of the book at the moment, at least the formal treatment. Now, this is difficult, and markets often work with a simpler formula where you assume that the defaults of S and B and the value of the underlying are independent. The same thing would be true for the case of an interest rate swap. And under the independence assumption, the formula is simpler. The CVA is now, the loss given default is out there, integral from 0 to t. That's a survival probability of firm B times the discount factor times the expected positive, so-called expected positive exposure, the expected value of the swap, and you integrate with the density of the default of S. So basically, if you say integration is a summation, you sum over all times the probability that S defaults at time t times the expected positive exposure, discounting, but you have to sort of a loss only if B didn't default before you. That's a simplified formula which you get under the assumption that the market value of the contract and the default times of B and S are independent, and the similar story holds here. Now, well, we're finally back to the theme of this week. I mean, if I would have to mention one sort of overarching theme of both this workshop and of our book, I would say it's dependence modeling and its implications for risk, joint extreme events, underestimation of dependencies, and perfect storm scenarios, or all that. It's difficult to have only one idea in a 600-page book, and it would be sad if it contained only one idea, but that's probably the main idea. And we are back to that now. An assumption of independence. What would you think in the case of the credit default swap or in the case of a reinsurance? Let's consider maybe a reinsurance treaty. You have a reinsurance treaty. Could you really assume that the default time of a reinsurance company and the value of the reinsurance contracts, the market value of the reinsurance contract, it has written that these things are independent? But not necessarily, the way I asked it. This is known as wrong-way risk. Let's take the other example of the credit default swap and assume that all three guys, as it very often happens here, so the reference entity, the protection buyer, and the protection seller are banks. So say the protection seller is whatever, Deutsche Bank, and the protection buyer is UBS, and the reference entity is whatever, Société Générale, to place it over 3 different countries. And now assume that the protection seller, Deutsche Bank, defaults. Well, it is very likely that Deutsche defaults. Okay, they might also default because they lost yet another lawsuit, but it is quite likely that they default because it's a situation where life is very difficult for banks. B, if Deutsche defaults because they made so many deals, it's very likely that the reference entity, which was Société Générale, comes into trouble. So this means that the value of a protection buyer position on Société Générale in this scenario, given that Deutsche defaulted, is quite high. Probably these credit spreads would, if Deutsche really defaulted, credit spreads would really jump upward if you think about what happened at Lehman's default. So they are definitely not independent in this case, and this is known as wrong-way risk. And if you want to really understand it quantitatively, how much that matters, we did this in one. You need then again a dynamic model, and you can then simulate these things and so on. You find that maybe it's around, underestimate the credit value adjustment by maybe 50–60%. Of course, banks know that, and they tried some adjustments there, but it's again a nice example, I think, of risk management in a situation where many things can go wrong together. That's what is written on these slides. Well, maybe if you want to know more, read nice books by John Gregory. They mix nicely mathematical modeling and also institutional features on these markets, maybe even more the institutional ones, but they are, of course, very important for counterparty risk management. Well, this brings me to the end of my presentation. I said there's a lot of similarity between credit risk and survival analysis, so you've survived it by now. And being the last speaker, I should say a couple of thank yous. I should say a couple of words, in particular a couple of thank yous. Well, our first thank you, and I think I can say this for Paul, Marius, and Alex as well, goes to you, the participants. You have been a very active audience. It can sometimes be a little bit stressful to get too many questions, but it is far worse to get no questions. Because then you're thinking you're speaking for an audience who's just thinking, when is lunch, what do I have to do, maybe I should do my email or whatever. And you've definitely been a very active, participating audience that motivated us, and a very patient audience. I mean, even I found it tiring to listen to my colleagues, and I knew the stuff. So thank you for that. The more important thank you, of course, goes to François and his team for organizing it, for making it the perfect week, for organizing the beautiful excursions, the lovely weather, and all of that. And I think he deserves a last round of applause for that.